Hello everyone. Today I'm going to show you how to construct an influence line for a determinate beam structure using Müller-Breslau principle. Okay. What is influence line? Influence line, it gives you, let's say that you have a bridge, and let's say that this is your abutment, and then these are your support. Okay, and then you have load, unit load, and this is your reaction at A, and this is your reaction at B, and we know that there will be a reaction AY. Okay, so influence line um, means that you are interested in finding the reaction at A, which is your response function, AY, how it responds when this load is moving through the bridge. Okay, so let's say that you are walking. I mean, walking is not a big deal. Let's say that because we have our weight is not heavy enough to change that response to the bridge. Let's say that there is a truck, okay, and the truck is moving through the bridge, and as it move, you know that the reaction at A will change. So influence line give you that how the AY or your response function will respond as the unit load is moving through the bridge. So as it move in this point, as it move, your AY how it responds. So that is what influence line means, which is just to remind you that influence line is not the same as BMD, because BMD, what it does is, let's say that you are taking a video of the load moving in a bridge. Okay, let's say that the load is moving in a bridge, and BMD, which is bending moment, it will take a snapshot of that video and say that, uh, and then will take a snapshot of that video. Let's say that the load is here, and then you wanted to calculate what is the bending moment along the whole beam, and we know that the bending moment diagram along the whole beam will be this. So this will be your bending moment diagram along the whole beam when the load is applied at midpoint. And I influence line is not shear force diagram, and the same thing, the shear force diagram for this beam will be this. So SFD also with the shear force diagram give you the response of the whole beam, of this whole beam, when the load is at midpoint. So just like you take a snapshot of a video and then you use the equilibrium equation and find what is the shear force along the whole beam. But influence line, it gives you the response of one particular point. In this case, I am interested only in the finding the reaction as the load move through the bridges. So that is what you wanted to collect. That's what you wanted to know, how the AY will respond, or the in reaction at A will respond as the load move from A to B. So that is called as influence line. So influence line has to do something with a moving load, whereas BMD or SFD has to do something with a static load. That means it is load is acting at a midpoint or anywhere in the beam, and then you perform the equilibrium equation and find what is the bending moment along the whole beam. Okay, so that is influence line, and you can also solve influence line using the static equilibrium, which means that you will take a multiple snapshot and then calculate their use the equilibrium equation and find what is the reaction at each and every snapshot that you take from the video. Or you can use Müller-Breslau principle. So what did Müller-Breslau principle state? That it state that the influence line for a specific response function, which can be your reaction, your shear, or your moment in a beam, is proportional to the deflected shape. That means it will be same to the deflected shape after you release after you release or uh, uh, you release that function, which means that when the constraint correspond to that function, which means that if you are interested to find the moment or the reaction at A, you're going to release that restraint, because restraint means there's a reaction. So if you remove that reaction at A, and applied a displacement, then you will get the deflection of the beam, and the deflected shape of the beam is equivalent to the response, or is equivalent to the influence line of the beam. Okay, so uh, um, you're going to remove the restraint either by and then apply a unit displacement or rotation. Unit displacement is mainly for shear and reaction, which you're going to see later, and rotation it's only meant for moment. So so that's what Müller-Breslau principle stated. So you have to remove the constraint or the restraint in the beam structure. Okay, so how do you apply a Müller-Breslau principle? There are three steps. First step one is to release the or remove the structural restraint. Okay, so if you're interested in finding the vertical reaction, then you have to remove, because these are, I'm just going to show you the three support that we have learned in structural analysis. There are pin support, and this has a vertical reaction. That means there is a vertical restraint, and this is a pin, and this is a fix. And in order to perform a Müller-Breslau principle, you're going to replace this with a guided roller, and then give a unit displacement. So this is called as your guided roller. Okay, so you're going to replace all this reaction using a guided roller. So you see that you are removing the constraint. Initially there was a constraint of them moving up, but now you have replaced them with a guided roller. You can move a unit displacement. So unit displacement, so this is unit displacement. So that's what Euler-Breslau principle said, that for any support for vertical or horizontal reaction, you are going to replace them with a guided uh, roller. And if it is a horizontal, then it has to be a guided roller will be in this form, and then you're applying a unit displacement. And if it is a vertical, then this is the way you apply. And then for internal shear at a point, let's say that this is a point that you're interested, what you're going to do is you're going to introduce what we call as the guided shear. And you're going to move, because we are going to follow every sign convention, which is a positive. That's why this is, we know that for a vertical upward is positive. That's why we apply a upward displacement, and for shear we have to apply a positive shear. So in this case we are going to apply a um, a positive shear in this direction, and this will move up, which means that this will go up and this will go down. And this also, the total displacement will be equal to 1, or unit displacement. Okay, so please remember that we are following the sign convention. So this is the way you're applying the direction. The left one will go down and the right one will go up. And what it mean by unit displacement, which means that this displacement a1 and this will displace by a2, a1 plus a2 must be equal to 1. So the total displacement has to be 1, or unit displacement. And for internal beam, what you're going to do is internal moment, sorry, for internal moment, if you're interested to find a moment at this point in a beam, and what you're going to do is you're going to introduce a internal hinge, because this beam has a moment, but now you release that moment by introducing an internal hinge, because internal hinge has moment equal to 0. That means it can bend easily. This beam cannot bend because we assume that it is infinite rigid, has infinite rigidity. That means you cannot bend. And so by introducing an internal hinge, you can remove. And the way you apply the direction is this: your right side will be clockwise and your left side will be counterclockwise. So this is the sign convention that we follow for positive moment, and this is sign convention that you follow for positive shear displacement. So this is, and then you're going to apply a unit rotation, which is theta is equal to 1 is equal to 1 radian. Okay, unit replacement, which is 1 radian. And what does it mean? It means that you're going to displace or rotate the right side clockwise by theta 1, and the left side by theta 2. So theta 1 plus theta 2 must be equal to 1. So that means it has to be a unit rotation. And so that's what here it say, that once you have released the constraint, which is for the support, you put a guided ruler depending on whether you are interested in vertical response or horizontal reaction. And then you, for here, you introduce this called as your guided slider. And then for moment you are putting the internal hinge, and then you applying a unit displacement like I discussed earlier, and then you apply a unit rotation. And then after that what you're going to do is you are going to determine the deflection. And so this is an unwritten rule. When you determine the deflection, make sure that you follow these two criteria. Like, despite following all this step 2 and step 1, step 2, and step 3, in step 3, when you determine the deflection, there is something also that you must take care or must keep that in your mind. One is, you cannot move the supports other than the point of interest, or if it is a hinge, which means that internal hinge, because your internal hinge can rotate and can move up, and also it can move down. Okay, if there's an internal hinge in your beam, then you can rotate, and you can move this hinge up or down, or rotate in any direction, whichever is applicable. Okay, so but make sure that you cannot move the other support. If there's any other support other than the one that you are applying Müller-Breslau principle, then those cannot move. And then second thing that you must remember is, you cannot break or damage or bend the beam. Okay, you cannot break or damage or bend the beam other than the point of interest, or if it is a hinge. So please keep that in mind when you determine the deflected shape of the beam. So let's do one example. So we apply all the step, and then we'll follow, and then we'll draw the influence line for the beam. Let's say that we have this uh, 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 simply supported. And also I forgot to mention you that the where is it, um, that where should I write? I write here. Okay, I'll write here that the influence line for determinate structure is always straight line. Okay. So please remember that the influence line for a determinate structure is always a straight line. Okay, so we'll keep that in mind. So we'll apply all the steps and keep that in mind, that you cannot move the support, you cannot break or bend the beam, and the deflection should be always a straight line. Okay, so for this example,